Hello everyone, I'm Norman Wildberger and thanks for joining me. Today we have something very exciting. We are going to summarize the basic understanding of algebraic calculus. It'll be a very quick introduction to this brand new way of thinking about this subject. And then we're going to apply these fundamental ideas to verify Archimedes' parabolic area formula in a specific example so you see exactly how it goes. So there'll be all kinds of interesting definitions and theorems that so many of you will see for the first time here. So the example that we're going to be looking at is this one right here. So our points P0, P1, P2, the de Castelao-Bezier control points of this de Castelao-Bezier curve, otherwise a DCB curve, are given by these values. P0 is the point 1, 4, P1 is the point 6, 7, and P2 is the point 8 minus 2. All right, and we're interested in comparing this parabolic arc's area here, determined by this DCB curve in green, and this maximal inscribed triangle. Okay, so in this case here, we can sort of compute everything because we know that this critical point corresponds to the parameter value t equals 0.5, and so we're able to explicitly give not just the original p points, but also the q points and the r point and the midpoint of the side. So there's q0, and there's q1, and there's r0, and there's the midpoint m. Okay, and so we have all these values here, and here are the various relations that connect these things. Okay, so the ingredients are all there. We just now have to be able to figure out how do we actually integrate a DCB curve. So now I'm going to introduce you to the basics of algebraic calculus. So this is a brand new way of thinking about things, very exciting, and it really offers a brand new opportunity for educators around the world to rethink this fundamental topic and present it in a more natural and ultimately more logical and arguably more powerful way. Okay, so what I'm going to do now is I'm just going to give you the bare bones definition. This is, of course, not a complete treatment. Okay, for that, you can take the algebraic calculus course, the open learning course, which is online. That's the best way. But if you just want to watch the videos, you can go over to the Wild Egg Maths YouTube channel, and all the videos there are in the algebraic calculus playlist. Okay, so there's a huge amount of information that you can access. And in the course, of course, we develop things I'm going to tell you about here, but in much more detail with lots of examples and applications and lots of other things as well. Okay, so a little bit of terminology to begin with. An oriented edge, okay? I'm going to use this notation in Scientific Workplace. So points A and B these are affine points, and if we have an arrow over it, sort of like a two-sided arrow, that'll be an oriented edge. And what that is the list AB. I can even make a definition here. Maybe I'll do that, okay? Just making it clear that this is the definition of what this symbol means. Now, this is not to be confused with the idea of a vector, okay? A vector, well, that's in Scientific Workplace a little bit challenging to do. So I use what's called a TeX field. You can sort of do an encapsulated TeX thing here. Let me just show you what that is. So there's this command, oversight right harpoon up AB. Okay, so that's a way of creating a more traditional vector arrow with just one kind of barb. Okay, so if I typeset this, so you'll see what the difference is. Let me typeset things. So I hope you can see this. So where are we? Down. Okay. Yes, we've done that. Okay, down here, if you can see this, oriented edge, there's the oriented edge AB, and here's the harpoon edge. Okay. So let's get rid of that. Okay, let's come back to our document. Okay, so we know what an oriented edge is. So an oriented edge is a list of points. And if you translate that, you get a different oriented edge. That's what makes it different from a vector. Okay, the key notion, the signed area of an oriented edge AB. So if A is the point A1, A2, and B is the point B1, B2, these are affine points, then the signed area of AB, the oriented edge AB, denoted with little s of AB, is by definition 1/2 of A1 times B2 minus A2 B1. Okay, so it looks like a little determinant of the 2x2 matrix that you get by first row A and second row B. And there's a half in front here. And geometrically, this is the area of the oriented triangle OAB. So it's crucial that you understand this starting point, that we are introducing area, first of all, precisely, using basically ideas from linear algebra, and underneath everything is really the notion of the determinant. Okay, so this is a determinantal approach to area, which is in marked contrast with the rectangular approach, where you define areas of rectangles as lengths times heights or widths. That requires a prior Euclidean metrical structure to define lengths. Okay, so in this approach here, it's a purely affine notion. We don't need any metrical structure. It's really just the underlying linear algebra and these vectors that we're really doing. So to really clarify that, let me sort of illustrate things with this little diagram. Here's a triangle ABC, okay? And here are the points A, B, and C. And there's the origin O. Now, if I just take the polygon here and ask GeoGebra what the area, it tells me the area is 9.43. Okay, so now let's look at the signed area. So let's just look at this first oriented edge from A to B, okay? Its signed area is given by this thing here. Let's have a look at what, here you can see the formula. So this is the x of A times y of B. So the x coordinate of A times the y coordinate of B minus the y coordinate of A times the x coordinate of B, all divided by 2. Okay, so that's the signed area of this edge here. And geometrically what it corresponds to is the area of this oriented triangle formed by the origin O, the point A, and the point B, going around in this positive direction from O to A to B, in that direction. Okay, so that has the value 14.15. Now, similarly, the signed area of the oriented edge from B to C, that's given by this quantity here. It's the signed area of BC. I've defined a tool, so now I can just input 2 points, and that turns out to be 9.82. So that's now corresponding to this signed area, the triangle OBC, that oriented triangle. And finally, down here, C sub CA is minus 14.54. What's that? That's the signed area of this segment from C to A, this oriented edge from C to A. So we have 3 oriented edges, this one, and this one, and they each have signed areas. The first one is the signed area of this triangle, the second one is the signed area of this triangle, and the third one is the signed area of this triangle going in this sort of negative direction because we're starting from C and going to A. And what we see over here, this S of ABC, it's the sum of these 3 signed areas. And the effect of that geometrically is we're taking this signed area, adding this signed area, okay? So that's effectively the signed area of the entire quadrilateral. And then we're subtracting what's usually thought of as the area of this triangle here. Okay? By adding the signed area of this, it's really like subtracting this area. And the net effect is that we're just getting the signed area of the triangle ABC. And that's 9.43. You can see that's the same thing as what GeoGebra calculates just for that polygonal area. Of course, it doesn't depend if we move things around. Okay, this 8.82 is still the sum of these 3 signed areas. Okay, so this is the approach that we take in the algebraic calculus, a very different orientation. Now we concentrate first on splines, okay, and the key concept is that of the signed area of an oriented edge, and then we piece them together to get the signed areas of splines, and in this case a closed spline or an oriented triangle. So now let me return to our introduction to algebraic calculus. So once we have the notion of the signed area of an oriented edge, then we can immediately define the signed area of a spline, of an oriented polygonal spline, which is just a list of more than 2 points. So say A0 is a point, A1 is a point, up to AN is a point. Then this ordered list, well, list is by definition ordered, is written with this spline notation, and we agree that its signed area is simply the sum of the signed areas of all of the individual pieces, starting from A0 to A1 all the way up to AN minus 1 to AN. Okay, so geometrically, this is the signed area of the region subtended by the spline from the origin O, which is the 0, 0. And in especially important cases when the initial point A0 equals the final point AN. That's like what I showed you with the triangle in the GeoGebra worksheet. In that case, this signed area is independent of translation. Ordinarily, this just signed area of a typical oriented spline is not translation invariant. You move the spline, the signed area will change. But if the spline is closed, then we get this nice cancellation like we did in the triangle case, and then it becomes independent of translation. It's really effectively just the signed area contained by this closed spline. Now, since right now we're just dealing with linear things, okay? So this definition of the signed area of an oriented edge AB can be restated in terms of a parameterization of a linear curve that goes from A to B. Okay, so suppose that our curve is, say, gamma of t, given by two polynumbers p and q, which are linear. In other words, they are just having two entries, a p0 and a p1. So this is p0 plus p1 alpha. It's a linear function, if you like, or a linear polynomial or linear polynumber. And q is similarly q0 plus q1 alpha. Okay, so then you can check that this formula that we've defined for the signed area of this oriented edge, well, first of all, we can introduce a little bit new notation. We can refer to this as the signed area of the spline, okay? But let's say this parameter t is actually going from t to u. So t corresponds to A, and u corresponds to B. Okay? Those are the parameter values that go from one endpoint to another endpoint. Then you can check that the formula gives us something that looks very similar to how we started, but it's now P0 times Q1 minus P1 times Q0 all over 2, that's a number, times the difference U minus T. Okay, so this is a way for us to just extend this sort of geometrical definition of a signed area to a more functional definition in terms of the ingredient polynumbers of our curve, admittedly only a linear curve. Now, when we examine this story and examine, what does this particular definition for these linear polynumbers, P, Q, and so on, what properties does it have? We find that there are 5 crucial properties, okay? And rather briefly, here they are, okay? There's normalization, which is a sort of like the simplest kind of case when one of them is constant and the other one is linear, and there are 2 values, a half and a minus a half. There's a natural additivity. If you go from T to U and then from U to V, that's the same as going from T to V. Okay. There's a linearity in the actual entries of the curve. So, for example, the signed area from T to U of P plus R comma Q, so that curve, which is sort of like the x, or the first component is a sum of 2 linear polynumbers. Well, that's going to be the sum of the corresponding signed areas, STU PQ plus STU RQ. And similarly, the other variable, and similarly, there's a scalar kind of rule. And then there are 2 rules that tell us what happens if we translate one of these curves. Okay, we translate by c in the parameter direction. Okay, or if we dilate the entire curve by a factor of c. Okay, so there are these two rules that tell us what happens in these cases. Okay, so one has to do some work in checking these and becoming familiar with them. But the crucial property now is that it turns out that it's these 5 properties that will allow us to extend this very simple kind of approach to signed areas to more general curves, which are not just linear. Okay, this is the crucial thing that ends up allowing us to finesse entirely the notion of limits and Riemann sums and in breaking things up into little rectangles and summing and then taking limits. We're not doing any of that. Okay, we finesse that entire story, which means that we no longer need an underlying theory of real numbers to support these limits, which conceivably could arise. Okay, and furthermore, in fact, it's more general. We can actually extend this now to much more general number systems, including to finite fields, which is quite interesting. Okay, so how does that work? How do we extend this story from these linear polynumbers to more general polygonally parameterized curves, or DCB curves? Well, we have to introduce 2 important operators, which, from my point of view, really properly should be attributed, I think, to Johann Faulhaber, a prodigious calculator from Ulm in Germany, who in 1631 introduced these concepts, perhaps a little bit implicitly, in his determination of formulas for sums of powers of natural numbers. This is all explained in the algebraic calculus course in some length, and it's very interesting what Faulhaber did. Okay, so the heart of the matter is that we can, following Faulhaber, define the derivative and the integral as operators, and we're going to call them capital D and capital S, okay? These are operators on polynumbers, okay? And they're given by these very simple rules that D of the polynumber alpha to the n is n times alpha to the n minus 1. That's a familiar derivative formula that you'll all have seen many times. And S of alpha to the n is alpha to the n plus 1 over n plus 1, the familiar integral formula that you've seen many a time. But the point is that we can define these things purely algebraically, independent of any geometrical connection with slopes of tangents of curves or areas under curves. And indeed, Faulhaber's interest was not in either of those directions. He was interested in calculating some remarkable formulas for sums of powers of natural numbers. And that's where these 2 operators originally made their debut, okay, before Newton and Leibniz. Okay, and so we're going to be following this. So we're going to call them the Faulhaber derivative, capital D derivative, and the Faulhaber integral, capital I integral. Okay, this integral operator will also have cause to define a relative version. So if we have 2 numbers, t and u, and there's no necessary connection between their sizes, so t could be less than u or bigger than u or equal to u, we define s sub t super u of p to be s of p at u. So evaluate it's a polynumber, so we can evaluate it at u, and then we subtract s of p at t. Okay, so I should say, of course, to extend these definitions to general polynumbers, we do so linearly because every polynumber is a linear combination of these powers of alpha, and so we just use the linearity to extend the D and the S operators to general polynumbers. Okay, so then one can prove purely algebraically what's usually called the product rule and the chain rule and the quotient rule, and we can also prove what we might call the derivative integral composition theorem. That relates what happens if you do an integration first and then a differentiation, or if you do a differentiation first and an integration. Okay, and so now I can tell you what the 2 fundamental sort of results are, which are in some sense the highlight of the Algebraic Calculus 1 course. Okay, so the fundamental formula is the following somewhat remarkable thing, I think, that there's exactly one way to extend the notion of signed areas, S sub t to u of pq, from linear polynumbers to more general polynumbers, satisfying the above 5 properties. So if we're looking for an extension of this linear signed area notion to the general story with polynumbers, but we should want that those 5 properties are satisfied, then there's only one way of doing it. And there is one way of doing it. And it's completely determined by this fundamental formula that just tells you what happens when you have P is just alpha to the M and Q is just alpha to the N. The answer is that the signed integral from T to U of alpha to the M comma alpha to the N is this number. N minus M divided by 2 times N plus M, so the exponents here, times U, which is the upper bound, U to the M plus N minus T, that's the lower bound, to the M plus N. And arguably you could say, well, if M and N are both 0, maybe this is problematic. Yeah, so if we actually look at the formula when these things are 0, then there's a 0 over 0 here. So we just agree that in this case, this is a 0. Okay, now once one has absorbed this, then one eventually figures out that there's maybe a more compact way of saying what happens for general polynumbers, okay? And it involves what I call the area differential of the curve. So if curve gamma is PQ, P and Q are polynumbers, then its area differential, let's define that to be del of gamma of the curve. It's P dQ minus Q dP. So here is Faulhaber's capital derivative. Okay, so we take the polynumber P, we multiply by the derivative of Q, and we subtract Q times the derivative of P. That's the area differential. And then the fundamental theorem is a kind of a generalization or extension of this fundamental formula. Okay, and it says that if you have a curve gamma, which is PQ, so general DCB curve, it's a polynomially parameterized curve, so P and Q are polynumbers, and you have 2 numbers, T and U, then this signed integral from T to U of gamma, which we can also write S sub T to U of P comma Q, it's what you get when you take 1/2 times the Faulhaber integral S from T to U of the area differential of the curve. So more explicitly, it's 1/2 S from T to U of P dQ minus Q dP. So from my point of view, this is the fundamental formula of the algebraic calculus. This is the true fundamental formula. Okay, so that's a huge thing. If you take the course, you will spend many weeks learning all kinds of things, and eventually you will understand all of this completely well, I hope. But I want you to appreciate that even if you haven't taken the course, the bare bones sort of logical structure is, as I presented it here rather concisely, is still reasonably accessible. Okay, we have very explicit formulas, and now we can apply these formulas, and I'm going to show you how to apply them, okay, to verify Archimedes' parabolic area formula in the special case that we started out looking at. All right, now let's put the algebraic calculus to work to verify Archimedes' parabolic area formula in this specific example. Okay, so here are the points P0, P1, P2, the control points. Here is this point R0, which is the apex of this triangle that we're interested in. And here's that parabolic arc. So let's first calculate the signed area of this triangle P0, R0, P2. Okay, so first order of business, the signed area of the triangle P0 and then R0 and then P sub 2, okay? And I'm going to put a vector on top of that just to remind us this is really a signed or oriented triangle, okay? We're going in this particular order. So how are we going to do this? Well, we are going to take the sum of 3 signed area of the segments of the oriented edge from P0 to R0 and from R0 to P2 and from P2 to P0. To make that easy, here's a little function that we can define, S. S of A, B, C, D is AD minus BC all over 2. Okay, so if AB is the coordinates of the first point and CD is the coordinates of the second point, then this will churn out the signed area. Okay, so let's do that. So the signed area, first of all, of P sub 0 to R sub 0. And I should put an orientation above that. Fine. Okay, what is that? That's going to be, so that's going to be S of, what's P0? It's 1 comma 4, and R0 is this 21 over 4. And so we'll just evaluate that. Okay, and then the next order of business is from R0 to P2. Okay, so now we have to take, let's grab this thing here. I'll get rid of the P0 at the front and put in a P2 at the end. P2 is 8 minus 2. 8 comma minus 2. Okay, there's that. And finally, we have to go from P2 back to P sub 0. Okay, so I'll grab this thing. I'll get rid of the first 2 entries. So now we just have, that's P2, and I have to go back to P0, which is 1 comma 4. Okay, so those are the signed areas of the 3 segments of this triangle, and so we can conclude that this oriented triangle that we have is going to be equal to the sum of these things. It's going to be minus 17 over 2 minus 85 over 4 plus 17 for a total of minus 51 over 4. We're getting a negative answer because, as you can sort of see in this case, we're starting here and then going here and then going here. So this is a negative orientation altogether. So we expect to get a negative answer. Okay. Areas in this algebraic calculus are typically always with a sign, and the sign is crucial. Without the sign, the whole theory doesn't work really properly. Okay, a big distinction between this and the usual calculus. Great. Okay, fabulous. Now let's calculate the area of the parabolic arc. Okay, from P sub 0 to P sub 2. Okay, so for that we are going to want to describe the curve. Okay, and let me remind you back up here at some point, we described the curve in a number of ways. Okay, yeah, so here's R0, right? R0 was the actual point that was traversing the curve. So a particular parameterization is, okay, well, say this is maybe the simplest one, okay? That's just the Bernstein form of the DCB curve in terms of the control points P0, P1, and P2. So let's use that. Okay, so there's the thing, and let's define P0. There's P0, we'll define that. There's P1, we'll define that. And P2, there's the third control point. Okay, now let's evaluate this thing here. Okay, we're getting a polynomial in the x and y coordinates. Let's simplify that. There it is right there. So we get the DCB curve. Let's call it gamma to be consistent. It has an x coordinate and a y coordinate where P is equal to this poly number right there, and Q is equal to this thing here. Okay, what do we want? We want to find the signed area of this thing. Okay, from what parameters to what parameters? Well, we're at P0 when t is 0, and we're at P2 when t is 1. Okay, so the parameters are just going from 0 to 1. It's a nice aspect of the DCB framework. The part of the curve in question is parameterized from 0 to 1. So we're going from lower bound 0 to upper bound 1 of this curve gamma. Okay, and we also allow ourselves to write that, if we want, in terms of P and Q. Okay, we want this. So by the fundamental theorem, this is, okay, what does the fundamental theorem tell us? It tells us that this thing here is equal to 1/2 of the Faulhaber integral from 0 to 1 of the del, the area differential of our curve gamma. And to be specific, what is that? So that's the same as, the area differential is just P times dq minus Q times dP. So that is what we have to evaluate. All right, so let's do that. So let's grab this area differential and sort of, calculate that thing first, okay? Now, so what is this thing? Well, P is this thing right here. Here's P. There's the P, I might put it in brackets. And now I have to multiply it by dq. What is the derivative of Q? Well, I'm just differentiating term by term. Okay, the derivative of t squared, the d of t squared is 2t, so this will be a minus 24 t, and then the d of 6t will be just 6, and the d of 4 is 0. So there's d of q. Okay, and now we subtract q, which is this thing right here, times the d of p. What's that? Well, there's a minus 6t. We're just following Faulhaber here, plus 10. Sound good? So that's the area differential, and let's simplify that. There it is there, it's simplified. Turns out not to have a linear term, but that's no problem. Okay, so now we can compute S of this thing here. What's the formula? It's 1/2 of this Faulhaber integral from 0 to 1 of this quantity which we have just calculated. Okay, so what is that? Okay, this is 1/2. And this is the Faulhaber integral, so it's the linear extension, so we have to multiply by minus 102. And what's the integral of t squared? Well, it's t cubed over 3. T cubed over 3. So when we evaluate that, let me put it over here. There'll be it's t cubed over 3 from 0 to 1. So we have to essentially do, I'll put it here, 1 cubed minus 0 cubed. Okay, that's the Faulhaber integral of this first term here. And then we have minus 34. Now we have to integrate t to the 0. What's that? Well, that's t to the 1 over 1, which is just t. So we have to evaluate it from 1 to 0. Okay, what is that? Minus 34, minus 34. Well, that's the signed area of this curve. Let's go back to the diagram and see what that geometrically is. What have we actually calculated here? So there's the origin here, which I unfortunately you can't see very well, but okay, there's the origin there, okay? And we have this curve. There's the curve right there. Okay, so what is the meaning of this signed area of such a curve from t equals 0 to t equals 1? Well, it's the exact analog of what we got for a spline. It's the area subtended at the point 0 of this curve. So in other words, if we drew a line from P0 to the origin, another line from the origin to here, then it's this this bigger area that we're getting. We're getting this entire area formed from this path, starting from 0, going up to P0, then along the curve to P2, and then back here. Okay, that's not exactly what we want. It's very close. Okay, we're interested in this parabolic arc. So what we have to do is we have to adjust by the fact that we've included this oriented triangle down here from the origin to P0 to P2. So included here is the signed area of the oriented edge P0 to P2. So what we want to do is we want to subtract that. Okay, so let's do that. Okay. So to get the area of the, maybe I should have signed area just to be precise, to make sure you are used to thinking of that. To get the signed area of the parabolic arc, we need to subtract the signed area of the segment from we said P2, P0 to P2. Okay, what is that? i.e., so we have to calculate the signed area from P0 to 2. So that's equal to S of, the other one was 8 minus 2. And what is that? That's minus 17. In fact, that's obvious actually from this, because the signed area from P0 to P2 is just the negative of the signed area from P2 to P0. If you change the orientation of the edge, then the signed area inverts or negates. Okay, so he got 17 up here, so it's obvious that we should get minus 17 here. Okay, so conclusion. So the signed area of the parabolic arc is, now in summary, it's minus 34, which is the integral. And now we have to subtract this minus 17 for a total of minus 17. And now, the question is this equal to 4/3 of the triangle area that we got? Minus 51 over 4. Is that a true statement? Well, the 4's cancel. 51 divided by 3 is indeed 17. So it's 17, so this verifies Archimedes' parabolic area formula in this special case. And if you think about it, and I hope you do, you'll realize that the actual orientation of the points wasn't really important. As long as we're consistent about orientation, we don't actually have to fuss around about where things are. It's a general argument that would work in any example. So we're in a great position now, having checked it in this special case, to think about the general proofs, that we're now able to actually prove this historically important formula in the general case, something which classical calculus doesn't seem to have spent too much time thinking about.